This lesson is on free energy and equilibrium. So we have delta G, that can be when our substances are in any state. And then we have the delta G zero. And this is our Gibbs free energy change when all the substances are in their standard states. So that means if we have a gas, it has to be at 1 atmosphere. And if we have a solution, it has to be at 1 molar. And there is a relationship between the delta G and the delta G zero. And that is that the delta G is equal to the delta G zero plus RT, the ln of Q. So we have to add this term to the delta G zero to get the delta G if we have any gases that are not at 1 atmosphere or any solutions that are not at 1 molar. All right, so this delta G zero, we can calculate this from our table of delta G zeros. This R, this is the ideal gas constant R, but we have to make sure we use the proper units. For this equation, we need to use 8.314 joules per mole Kelvin. So we don't use the liter atmosphere. We have to use joules because we're dealing with energy in joules. So as usual, this is our Kelvin temperature. And this Q, we've seen this before. This is just the reaction quotient back when we did equilibrium. It is the same thing. So this is the equilibrium expression, the K, but at the concentrations or pressures that you are at. And our Q is always moving towards the K. Everything goes towards equilibrium. And everything goes towards a delta G value of 0. All right. So let's take a look at this equation and evaluate it in terms of what happens depending on the value of our Q. So when our Q is less than 1, then the ln of Q, if Q is less than 1, we have a fraction. Of course, it has to be greater than 0. We're going to have all positive values for concentrations or pressures. So our ln of Q is negative. The ln of a fraction is negative. So that means that our delta G will be less than our delta G zero. So if this is negative, this will be even more negative, which means we will have more of kind of like an oomph to get to a delta G of 0. All right, so if our Q then is greater than 1, then our ln of Q is positive, and our delta G is greater than the delta G zero. Because R is always positive, T is always positive, the Kelvin temperature. So if this is positive, we're adding to delta G zero. So we're getting more positive. So remember, the less positive you are, the more negative, the more spontaneous the reaction is at that point. All right, and then of course we have when our Q is equal to 1, well, then the ln of Q is 0. The ln of 1 is 0. And that means that our delta G is equal to our delta G zero. So that means that we are in our standard state. Okay, so now we're going to take a look at what happens when we are at equilibrium. So at equilibrium, our delta G is equal to 0, and of course our Q is equal to the K. We're at equilibrium. So we take our equation, the delta G equals the delta G zero plus RT, the ln of Q. And now we're going to substitute in our equilibrium values. So our delta G is 0. This equals the delta G0 plus RT, the ln of K. So this is at equilibrium. So we can solve for delta G0. So our delta G0 equals minus RT, the ln of K. So we have related our thermodynamic quantity to our equilibrium constant. So thermodynamics goes hand in hand with equilibrium. Neither thermo nor equilibrium tells us how fast our reaction occurs. That is kinetics. So we might go to equilibrium really quickly or really slowly. This, our delta G and K, does not tell us that. All right. Now, as a system goes to equilibrium, as we know, if we're out of equilibrium, we're going to go to equilibrium. So as the Q goes to the K, delta G goes to 0. It is 0 at equilibrium. So we say that the maximum possible useful work obtained from a process at constant temperature and pressure is equal to the delta G. So if we're at equilibrium, our delta G is 0, and we're not going to get any useful work. But if we are not at equilibrium, as the process goes to equilibrium, then we're going to get work out of that system. And we're going to see how that operates when we do electrochemistry. We can light light bulbs. We can do all sorts of work when we have a system that has a delta G other than 0, or we are not at equilibrium. So now we'll look at a problem. So we want to calculate delta G for the reaction 2H2S, hydrogen sulfide, plus sulfur dioxide, yields 3 sulfur in the rhombic solid state. We have rhombic and monoclinic. The rhombic is the standard state of solid sulfur, and 2H2O gas. And we're given the following conditions. We're given pressures of our gases. So to calculate delta G, we need to calculate delta G0, and then we need to calculate Q, and then we can use our delta G expression. So let's calculate our delta G0 first. So delta G0 is equal to the number of moles, so 3 times the delta G0 formation of solid sulfur in the rhombic state, plus 2 times the delta G0 formation of H2O gas, minus 2 times the delta G0 formation of H2S gas, plus 1 times the delta G0 formation of SO2 gas. So just our Hess's law, like we've been doing with enthalpy for a long time. Okay, we go to the back of the book, look in the appendix, and get our values. So this is 3 times. The sulfur is the standard state, and so that is 0. So that just goes to 0. Plus 2 times, and this is a negative 229 kilojoules, minus 2 times negative 34 plus negative 300, and that's all in kilojoules. I should make that brackets. Okay, so plug that into your calculator, being very careful about your signs, and you should get a value of negative 90 kilojoules, and that would be per mole of reaction. Okay, so that's our first part. Now we need to calculate our Q. So Q equals, so it equals, this is a solid, doesn't show up in the expression for Q. So we take the pressure of H2O gas squared over the pressure of H2S gas, oops, that should be a small s, I don't know why I wrote that as a large S, squared times the pressure of SO2 gas. So our Q, the pressure of the H2O, so this is 3.0 times 10 to the negative 2 squared over 1.0 times 10 to the negative 4th squared times 1.0 times 10 to the negative 2. So calculate that out. Well, 3 squared is going to be 9 times, this is negative 4, negative 8, negative 2, and you should get times 10 to the 6. So now we can substitute in to our equation. Okay, I thought I was going to have enough room on that one paper. So our equation is delta G equals delta G0 plus RT ln of Q. All right, so delta G equals, we just calculated delta G0, negative 90 kilojoules, plus R. Now R, our value of 8.314, that is joules per Kelvin. So I'm going to change that to kilojoules. I must have my units that match. So R is 0.008314 kilojoules per Kelvin. Our temperature, of course, has to be in Kelvin. Our problem told us we were at 25 degrees C, so that is 298 Kelvin times the ln, and our Q we calculated is 9.0 times 10 to the 6. So plug all that into your calculator, and you should get negative 50 kilojoules per mole of reaction. So our delta G under our conditions has a value that is not as negative as its standard state. So we're closer to equilibrium here than we would be if our gases were at 1 atmosphere. Okay, and we'll look at our final problem. Calculate the delta G0 and K at 25 degrees C4. All right, so this is the same reaction. So we already calculated our delta G0 for that. So delta G0 equals negative 90 kilojoules per mole of reaction. And we want to calculate K. Well, we have our delta G is the delta G0 plus RT, the ln of Q. And we know when we're at equilibrium, this is K, this is 0. So we get delta G0 equals minus RT, the ln of K. So our delta G, negative 90 kilojoules equals negative. R again, make sure you put that in kilojoules, 0.008314 kilojoules per Kelvin times our temperature, 298 times the ln of K. So first I'm going to solve for the ln of K. And when I did that, I got 36.32. Yeah, it's extra sig figs, but that's all right. So now to solve for K, we take E to both sides. So K equals E to the 36.32. So our equilibrium constant equals 6.0 times 10 to the 15th. So this tells us that equilibrium lies far to the right. Then we end up with mostly products. So now we have a way to figure out our K if we know the delta G or vice versa. That's it.